Hi, I'm Chris Allen, and I'm going to be presenting to you today information on the LZOP compression protocol and its use in the Hadoop distributed processing MapReduce system. To give you a quick overview, we'll talk about what LZOP compression is and how it slots into Hadoop. We'll kind of explain the hardware scenario that has produced this situation where it's used, namely discussing the relationship between system I/O and CPU cycles on most computers now. We'll discuss what indexed LZOP is and how it differs from traditional compression. We'll go through installation and usage instructions, results and analysis, where we will use compression on a variety of data sets and compare how long it takes to produce a result compared to a non-compressed data set, and then get into conclusions, try and figure out, is there a general rule of thumb for where LZOP compression is worth applying in Hadoop MapReduce jobs? First being, what is LZOP for Hadoop? And this is, LZOP implements the ability to stream data from a compressed file. Our individual MapReduce tasks can flawlessly and invisibly to them read data from compressed files that as they read it is then decompressed and provided to them as exactly the data they're expecting. In our setup, we compress the file and index it, which is important because this indexing allows individual map tasks to just pull, whatever block they need. Because if we recall, MapReduce involves, multiple mapping tasks kind of crawling over our gigantic single large data file, pulling pieces willy-nilly, and this means that they will not have the top of the file, which would have a traditional compression header. We index it so no matter where the MapReduce task pulls data from, it is then able to decompress it. And in a nutshell, why we do this is for I/O heavy tasks, tasks where we're reading in a lot of data and not performing that much computation on it. It's actually faster to precompile or pre-compress the data, index this file, and then decompress it live as we read it in. To give you a kind of technical background on why pre-compression has become a thing, it's kind of related to Moore's law, the exponential growth in CPU cycles. CPU cycles are incredibly cheap, but you can always buy more processing power. Disk I/O, however, reading from your hard drive, writing to your hard drive, has always been and still is relatively a very expensive operation. Anybody who works with operating systems knows that, the holy grail of optimization is avoiding page faults, where you say, oh, shoot, I don't have that thing that you want loaded into my RAM. Let me go get that from the hard drive for you real quick, which it turns out is not real quick. It takes a lot of time. So assuming that time is our limiting factor, what we care about, it makes sense to compress these files in advance and then decompress them on demand. This system is actually already in widespread use, generally, under the hood where you're not going to be aware of it. The OS X operating system, for example, all their files are compressed on disk and decompressed as needed. Next, discuss why we used LZOP versus a more traditional compression algorithm. LZOP compression is designed to minimize decompression time because while we are interested in reducing the amount of time we read and write, we don't want to then waste all of that time compressing the file. Systems like gzip or tarring a file were designed with transmitting that file over a network in mind, where bandwidth is an incredibly valuable thing and it's worth it to spend a little more time to compress it before you send it out. We're not dealing with that. We want kind of a quick and easy decompression that doesn't have to get it as small as possible. And you can see here this example data compressing a 5 gigabyte file. LZOP produces a larger file, but it compresses it in much less time, and it decompresses it in significantly less time, which is ideal for our task. There are implementations of compression on Hadoop that use other compression algorithms, but LZOP seems to be the most widely adopted. Next, into why traditional compression doesn't work with Hadoop jobs. We've discussed this earlier. Hadoop assumes files are homogeneous, namely that the mapping task can pull a block of data from anywhere in the file and then proceed to work on it. However, when you compress a file, if you create a gzip file or a tar.bz file, it's got a compression header at the top that has in it the decompression data that you need to return to the original file. If our Hadoop task pulls a chunk of a bzip file, it's not going to know what to do with it. So indexing solves this issue. What we do is we essentially take that large zip file and we seed it with the decompression header at specified intervals. And we create an index file that sits in the folder adjacent to it and basically has the addresses of all of those decompression headers. So when your map task says, I'm ready to process another block, I want to grab from, using rough addressing, I want to grab from 5,000 to 7,000 to process that. The Hadoop framework steps in and says, you can't do that because you're not going to be able to read it. But if you take from 5,500 to 7,500, that's a block that has a decompression header in it, and you'll be able to read that in. And then it consumes that block flawlessly and invisibly to our map task. Getting into installing our LZOP, just to give you a very quick run through of the challenges involved, what I ended up doing is downloading the code from GitHub, installing several yum packages, having to modify source code in the install, set compile flags, build the project, copy binaries to Hadoop, copy the jar to Hadoop, and update several XML files. Difficulty of this I would describe as moderate. The only challenge being that I had to implement bug fixes that other people did and I was able to find via Google, thankfully. But these bug fixes had not been merged into the trunk, the actual code that you get when you go to GitHub and click download zip file. This is a little concerning because this means that the project hasn't been updated in over 2 years. Using LZOP in our Hadoop framework makes up for that, though, because it's pretty elegant, I've got to admit. And how we do this is we copy our data set and send it to the HDFS system. So we can make our directory and take our LZO file, which we've just compressed using the command line utility LZOP, and send it to input. We then index it, and indexing is actually just done as a separate Hadoop job. And we can run that using, like we've done before, the Hadoop jar command. We use the jar that we built following the installation instructions. And then it'll index the file. And this takes a very, very small amount of time. We then take this LZO jar that we created, and we can add it to our task jar. We've got experience with building jars to perform Hadoop tasks, and then running them via the Hadoop jar command. One of the things that we can do to streamline our task then is that the system will automatically check in that jar in the lib folder for anything that it requires to perform its task. We could go and install LZO on all of the nodes that we're running on, but assuming we're running on the same system architecture, we can just build on the master, package this jar, and include it into our task jar. And since I've just been using the word count example, I packaged it into our Hadoop examples.jar. And after this, we execute it using an exactly identical system to the way we did before. Hadoop, jar, word count.jar, input directory, output directory. And the cool thing about this is once you've built the package, once you've added that thing to the jar, it's done. It's invisible. You cannot tell the difference in the end output from operating on compressed data versus operating on uncompressed data. The system automatically detects it, decompresses it, and passes it to the task. The same jar can be used seamlessly for uncompressed or compressed data. The one thing that I do want to point out, though, is that this was all done on stuff using the old 2.0 API. I was unable to get this to work with the newer API, and a lot of people using Google are having similar issues. And again, this project has not been updated in 2 years. It becomes questionable, is there a problem with the source code that would need a fix, like I had to fix to get the project to build in the first place? Or is it just a matter of you need to Google more and bang your head against it longer? So while it was very easy to use in the 2.0 or 0.20 API, I would have concerns about using it if you wanted to apply this to a task that you had already written in the new API. So, we've gone through all these hurdles, we've jumped through all these hoops, implementing this package and installing it. What do we have to gain by it? And again, I'm using this all on a data set that everyone in the class has already worked on and should be familiar with as a nice comfortable baseline, the word count problem operating on that Bible file, which was about a 5 megabyte text file. So my very first run, I operated on that data set. And as we can see here, I end up actually getting a less efficient file, or less efficient time than I had initially. I end up gaining 5 seconds. And my end analysis on this is that it takes time. Hadoop has a large time to spin up. You can see this if you look at the log files as they scroll by. And essentially loading those libraries and packages and then doing the decompression eats up any time we save by decompressing the files. However, big data is not 5 megabytes. Big data gets into terabytes size. So, I don't have time to do processing on terabytes of data, but what if I take my system and I update it from 5 megabytes to 5 gigabytes? So what I did is I took that Bible file and I just copied it, appended it onto itself 1,000 times. And then running this, we get a nice significant result. We end up going from a 5 gigabyte file taking 30 minutes to run on an uncompressed system to 21.6, which, a 30% reduction in runtime is tangible and certainly could, for a lot of users, justify the implementation of this. However, one additional thing to look at is not everybody's going to be operating on a data set that's the Bible copied 1,000 times. Some data compresses well, and some data does not compress well. And this is getting into information entropy, the fact that in some data, you don't need all of it to represent that. The human language has low information entropy. We have a lot of words that repeat themselves. We have a lot of letter patterns that repeat themselves. We can see this ourselves. You can take a sentence and pull a word out of it and present it to a stranger, and a lot of the time they'll be able to infer what word should be there, just as kind of a conceptual example. But, some data does not compress well, and this touches on the pigeonhole principle, which we all covered if we took CS. If you took an entry-level CS class, the pigeonhole principle is basically I cannot map n things to less than n things without having overlaps in those. I can't put 20 objects in 10 mailboxes without having some mailboxes with multiple objects. If every file was able to be compressed, to be able to be mapped to a file smaller than itself, some small files would, of necessity, be decompressed to 2 different output files, which is not what you want. When you unzip a file, you want it to produce one thing every single time. So I kind of automatically skipped straight to the worst case scenario here, and I created a 1 gigabyte file of random gibberish that I just created from the Linux dev random prompt. And when I compressed this, it actually grew slightly, which makes sense. Your system should not be able to compress random data. If you come up with an algorithm that can compress random data, I recommend you patent it and make a lot of money. And running the LZOP Hadoop word count job, we actually gain, it takes a minute longer to run than the uncompressed task. This makes sense, again, as the compressing and decompressing is only adding overhead. Let's say my task reads in 100 kilobyte it needs 100 kilobytes of data. It's going to have to read 100 kilobytes of compressed, air quotes, data off the hard drive and then decompress it to do anything with it. In conclusion, we can ask where LZOP is worth it. Where this is worth it for you, the IT person, worth it to implement on your enterprise scale solution, or worth it when you're messing messing around at home and you want your jobs to run a little bit faster. It's worth it if your data is large enough, multiple gigs, compresses well, and you can test that just by zipping it, and you're comfortable with running it in the old Hadoop style API, or you're okay with figuring out how to get this to work in the new API. It's not worth it if you're at all concerned about support or the system breaking as the project is abandoned, and it's not worth it if your data is small or is in a format that doesn't compress well. This still leaves a lot of cases where this works, and I think this would be a valuable tool in anyone's tool belt for doing, large-scale data analysis in Hadoop. Thank you very much for your time.